AIM 11.8 Exponential, Power, and Logarithmic Regressions. Your homework tonight is Delta Math. Scrap paper is required. And when I say scrap paper, I want you to show the computations and how to find the answers algebraically. Simply using a table is not sufficient. I want to see that you can actually derive these answers algebraically, use the calculator to get the regression equation, but then from there, you're solving the problem. If you don't do that, I will not award credit. Okay, so an exponential regression. So here we have the accompanying diagram, and we're given that the number of bacteria in a certain culture, this is over a 5-hour period, where X is the time in hours and Y is the number of bacteria. So we have to write an exponential regression equation for the set of data, rounding all coefficients to the nearest hundredth, and using this equation, determine number of bacteria present after 9 hours to the nearest whole number. So you're going to enter in this information in your calculator, clear your lists, L1, L2. If you have any questions about that, please review the past lesson 11.7 as to how to enter the information in. So in order to enter in the information, we're going to go down to exponential regression, or exp-reg, and that would be the one that you select. Make sure that your stats diagnostics are on. And we get the following, that our A is 86.36 and our B is 1.17. And this is for the equation y is equal to ax, a times b to the x. So we plug these numbers in, and we get that y is approximately 3,559. Okay, so now exponential regressions with logs. So again, we have to figure out the following problem. A car over time, it was purchased for $16,100. X represents the number of years, and Y is the value of the car in dollars. Most cars, unless it's a classic, can depreciate with age as soon as you drive it off the lot. So write an exponential regression equation rounding all coefficients to the nearest 10,000th, so that's 4 spaces past the decimal. Using your equation, determine how long it would be to the nearest 10th of a year. So please make sure that you're rounding each part appropriately until the car gets to be worth $2,100. So you are your own Kelly Blue Book, if you will. So when we enter in this information, we get the following. Oh, but wait, now we have to figure out the time span that this would be. How long would this take in a matter of years? Notice though how we have an exponent that's unknown. So in this case, when we have to solve for an exponent, that requires that we introduce a logarithm. So we divide each side by 16,356.3803. And when we do that, we get approximately what is on our left side, 0.12837. And that is equal to 0.828 raised to the x. If you incorporate logs on both sides, we can use now the power rule of logs, and the x portion comes down, and now we can isolate the unknown by dividing both sides by log 0.828, and we get that it's approximately 10.9 years before the car is worth $2,100. Now, a power regression, similar to an exponential regression. However, power regressions don't increase at the same rate, not necessarily at the same rate. They don't increase as steeply as an exponential regression. They will increase, just not as fast of a clip. Okay. So after an oil spill in the ocean, oil continues to leak into the water. In the accompanying table, X represents time in hours and Y represents the diameter of the spill on the surface in meters. Write a power regression equation for this set of data, rounding all coefficients to the nearest 10,000. Using this equation, find how much time has passed to the nearest 10th of an hour if the diameter of the spill is 101 meters. So again, notice what's highlighted: a power regression, round all coefficients to nearest 10,000, and our final number should be rounded to nearest tenth of an hour. It's important, this is as much a reading comprehension problem as it is a math problem, because you have to execute the following things in this manner. So for a power regression, we're going to go down to where it says power reg. So we enter in the information as it's given in that form, and we get the following. So here we isolate by dividing 98.2856, divide both sides by that, and we get our number on the left. And we have to solve for x. So the easiest way in order to solve for x when it is bound by an exponent is to raise everything to the reciprocal, because when you raise everything to the reciprocal, this will simply become 1, so it'll become x to the first. And you've thus isolated x. So we do this to both sides, and we get that x is approximately 16.2. So now a logarithmic regression. The accompanying table shows the wind speed and the corresponding wind chill factor when the air is 18 degrees Fahrenheit. Write a logarithmic regression equation for the set of data, rounding all coefficients to the nearest thousandth. Using this equation, find the wind chill factor to the nearest degree when the wind speed is 27 miles per hour. So here, this is important. You need to look for the one that we're going to use a natural log. We're not using our common log, but natural log. So we're going to use ln. Now there's another option under this menu. If you continued on, it says logistic. I know it starts off with log, but that is not what you want. You want the natural log regression, so ln reg. So we use this information and we plug in to find our unknown, and we get that y is approximately, if our wind speed is 27, y is approximately -5. And